Right. Now let's continue our discussion on the statistical hypothesis testing methods available for machine learning purpose. So there are, in fact, many testing methods are available, but as far as the machine learning is concerned, some of them are favorite. So we need to work on the data when it comes to machine learning. Then we do need to do some statistical tests. For this, we define some hypothesis, then verify whether our hypothesis is right or wrong. Basically, there are five types of five types of hypothesis test. We prefer to work on data for machine learning. One is a normality test. So it is to check whether the data we have has a Gaussian distribution or not. Then we have correlation test. It is used to check whether the two samples are some way related or not. Then we have a test for time series data. That's a stationary test. It checks whether the time series is stationary or not. That means whether it contains any trend or seasonality. So that's a test we have for finding whether the time series data is stationary or not. Then we have some parametric statistical hypothesis tests where used to compare the data samples. Here the comparison is done through parameters of the distribution, and we have another set called the non-parametric statistical hypothesis test. So these are the various statistical testing methods described in the paper mentioned here, machinelearningmastery.com statistical hypothesis testing. It's in the Python cheat sheet. So thanks to the author for compiling all these 17 methods at one place, and I'm trying to put that in a form of a video. So the first thing we need to look at our data is that assumption that the data is independent and identically distributed, or in short we say IID. The collection of random variables is independent and identically distributed if each random variable has the same probability distribution as the others. That means if you say that two random variables are there and both the random variables have similar probability distribution, then we can say they are identical and they are mutually independent. That means data from one variable does not affect the data on the other variable, or the outcome of one experiment does not affect the outcome of another experiment. So we say that they are independent. So when it comes to independence, then yes, of course, we get a liberty to use this mutual independence for computing the joint probability as a product of probabilities of each one. So this computing product usually is a bit time consuming when it comes to machine level. When you look at these at machine level, yes, of course, it is going to be higher time consuming. Therefore, instead of multiplication, if we can use addition, it would be much faster. So the best way to convert a multiplication into addition is through logarithm. So if we take logarithm, then the products become sum. And then we can make use of the maximum of the value of theta, for which we get a maximum log L of theta is what we are searching for. So example of IID. So toss a coin 10 times, record how many times does the coin lands on head. So we toss the coin 10 times and then record how many times we get a head. We say this experiment is independent because each outcome of landing will not affect the other outcome. So if we get first head, then you can't claim that next should be head or tail. So they are independent. So nothing like there's dependency. So all 10 results are independent from one another. So the one experiment or one toss will not affect the other one. Then identically distributed. So as long as the coin is fair, then each time the probability of getting head is 50% only. Therefore, the experiment, any number of times you conduct, you get a probability of getting ahead 50%. So that's identically distributed, 50% head, 50% tail all the time. And each experiment is independent of one another. So this whole process of tossing a coin some number of times is an IID. Or you can think of choosing a card from a standard deck of 52 cards and then place the card back. Repeat this any number of times. Then find out how many times king appears. So we are replacing the card. Therefore, every time there are 52 cards in our deck when we are conducting an experiment, and hence it is independent because it doesn't depend on the previous one. Instead, if you don't place it back, then for the first time you are drawing from 52 cards and that card is set up apart, and then tried second round. Now in the second round there are only 51 cards. Therefore, now the things are not independent. They are dependent on what happened earlier. If one card had gone earlier, which was already a king, then the next time you are left with only 3 kings. Same way, they are identically distributed because every time all 52 cards are used for experiment. Therefore, each time there are 4 kings in the card. So probability of getting a king is always 4 by 52. So that is identical each time. This picking a card from the standard deck of card becomes IID only if you replace the card back to the deck after every experiment. If you don't, then it can't be IID. Yeah, that's a symbolic explanation about IID dataset and non-IID dataset. If you can see that the left side we have IID dataset where we are doing 2 experiments. In this first experiment, we keep on drawing the numbers randomly and we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All 9 numbers we are getting. Whereas in the second case, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 is in the first case, 0 in the second case, 1 is there first case, 1 is there in second case. So you can think that 1, 0 to 9 are there in both the experiments. But if you look at the non-IID data set, then in one data set you are getting only zeros and fours, whereas in other data set you are getting 5, 7, So we can't claim that the two experiments might be from the same data set. So there is no common in that thing. So you cannot say that they are independent. They are identically distributed. If you look at first case, zeros and fours are there. So 4 zeros, 5 zeros and 5 fours are there. Whereas in the second case, 5 fives and 5 sevens are there. Yeah, the distribution is totally different. So they are not identical in distribution. So that's what we can explain about IID dataset, non-IID dataset. And most commonly, we are working with IID datasets for our